Hello, this is Mike. Welcome to another Nastran validation. What we're looking at today is a 1/8 section of a torus. If I rotate that around, you can see we have a 90-degree swept or revolved section. The full torus, of course, would include the other 3 or 270-degree section of that plus the bottom half. We're just dealing with the top half here and 90 degrees of it at that. And then we can apply the symmetry here, which of course will help with stability of this model. If you wanted to look up the resource, if you have a 5th edition Rorks, this is page 454, table 29, case 5A. And again, it's a 1/8 model. The outside diameter is 30.4 inches with a width of 10.4 and wall thickness of 0.2. I'll show you the sketch here in just a moment. We are going to assign an internal pressure of 35 psi, and then the target stress that we're looking for is a 1312.5. So as far as the sketch is concerned, let me right click on the sketch here. Pretty simple geometry. I'll just open that up. So created a circle, made it 10 inches over from the origin, and the diameter on that is a 10-inch circle, and then created another circle. Diameter on that is 10.4 inches. And then basically I just drew a horizontal line and trimmed off the bottom halves of those two circles, and then capped off the ends here. And again, the center of those circles is 10 inches out from the origin. So that is the sketch that you begin with. And then of course, we just revolve that 90 degrees in the negative direction about the y-axis. So that's how the geometry is constructed. Let's go ahead and take it over into Nastran and see how we compare to, well, how do we set it up, and then how do we compare to the theoretical value. So I'm going to go to the Environments tab, and off of Environments, we're going to go ahead and select Autodesk Inventor Nastran. And as soon as that comes into Nastran, one of the first things that I typically do is define the material. It's one of the first things here in the model tree, so I'm going to go ahead and expand the solid. By now, if you've watched a couple of these videos, you know that if you import a solid or move a solid into the Nastran environment from Inventor, it creates the solid idealization for you. And then if you have defined a material in the Inventor workspace, which I did not, it'll even bring in that material for you. But I didn't define a material there, so I'm going to go ahead, right click on that, and what we can do is either type in the values that we need, appropriate values for a linear static model, or we can go into select material, and I'm just going to select something from the Autodesk material library. I'm going to scroll down and take a steel ASTM A36. So I just passed it up. There we go. So, there's the typical properties: modulus 2.987, the yield, of course, at 36,000, and we'll say OK. So now we have the material defined. I could either mesh the model, or we could start to apply our loads and constraints. I'm going to do constraints first. So let's go ahead and select the constraints. And much like the other videos, when we slice through, where I've used symmetry, when we slice through geometry, what we have to do is select that face that is a cut face where we slice through the geometry. And then Nastran has some presets here for symmetry. And the vector that you choose is whatever vector is perpendicular to that face, right? So you can imagine in the full model, this face that I just selected wouldn't exist, right? You would just have the outside shell and the inner shell. So because this is a cut face, if you will, I need to define that as a symmetry plane, symmetry face. And again, the vector that is perpendicular to that one is the Z. So I can choose Z symmetry here for my constraints. And you can see that the program goes ahead and constrains the translation normal to that face, and then the 2 in-plane rotations for me. Now, if I want to keep things organized, I can assign a name to this constraint, and I think I'll go ahead and do that. So let's call that, I'm going to call that Z sim, and we'll say OK. So the reason I'm doing that is now you can see in the model tree, it has that name. So that way, whenever I do my other ones, let's go ahead and select this face over here. and that would be what? The X is perpendicular to it, right? So that constrains the out-of-plane translation to in-plane rotations. Let me assign that name. So what I was saying right before that is, as I get multiple constraints over here on the left-hand side in the model tree, because I'm assigning them names, if I need to modify them, I can quickly go through and figure out which one's which. And if I say, okay, I needed to edit the X symmetry one, then I can just double click and choose to edit it. So I don't always name the constraints or the loads in my models, but whenever I tend to get a lot of different loads that I'm applying to a model, or when I have a lot of different constraints that I'm applying to a model, then it just helps keep things organized if I need to go back and find something over here and edit it later. So we have our last two symmetry constraints that we need to add here. Let me select that face and that face right there. And of course, maybe I'll rotate that around. You can see, looking at the mini axis down here, the y-axis is perpendicular to those faces. So I'm going to select Y symmetry, and again, we'll name that just to keep everything nice and organized. All right, so there's my X symmetry, Y symmetry, and Z symmetry. So, by virtue of those symmetry constraints, we have accounted for translations X, Y, and Z without adding additional artificial constraints into the model that will negatively impact the results that we get with this model. So it's one of the cool things. If you have been watching the videos, you know by now I am a fan of symmetry. So let's go ahead and apply the pressure on the inside of our model. So I'm just going to select loads up here at the top. And there's all the different types of loads that we can apply to a model. In this case, it's just the pressure, and that pressure is 35 psi. Come over to select the entities, and I'm going to select the face on the inside of that model. So there's the 35 psi. We'll say OK, and there we go. We get a pressure glyph indicating that there is a pressure applied to that surface. See, I didn't name that one. Of course, if I do hover over it, it does give me a little bit of a tip about what that load is. It's telling me it's 35 psi, but I didn't assign it a name. It's just a generic load 1. You can also name the loads that you apply. So if I wanted to assign the name, we'll call that internal pressure and say OK. There we go. So that way, if you had an internal pressure and an external force in a moment, you kind of get the idea. I could, readily identify which loads are which here in my model tree. So just kind of a neat little feature. As far as the mesh is concerned, I'm just going to go ahead and hit generate mesh and take a look at the default mesh, right? And looks a little bit coarse. If you want to change the mesh in Nastran, it's super simple. We're just going to go into mesh settings. And again, you can adjust the slider, or you can type in a mesh size. So I can see that the mesh size that's on there is about a 0.8 inch mesh size. So if I want to go about half of what that mesh size is currently, for instance, we can go 0.4, and I'll say generate mesh, and that gives me a nice fine mesh that should be sufficient to bring our results within realm of the solution that we are looking for without getting to be too large of a model. Speaking of the size of the model, as you mesh your model with different sizes, notice here in the model tree, it does report how many nodes and how many elements you have at a given time. So with this mesh size, I can see that I have 23,000, about 24,000 nodes, and about 11,700 elements. So let's go ahead and run it. I think this will be fast enough. I don't need to pause the video or anything like that. So this will give you an idea, about how long it takes to run a model of that size. And I'm just running on a laptop here. It's a laptop that's several years old, so nothing too crazy. And you can see that that runs rather efficiently. So here we are in the results environment, and I can see the deformed shape, and we can see our stress values. The way that we're going to interrogate the results from the pull-down menu at the top, that you can change from looking at stress to displacement or strains, reaction forces, etc. We do want to look at stress, so I'm going to leave it on that selection. But what we want to take a look at is the Y tensor. So from the pull-down menu, I'm going to change it from currently displaying a von Mises for me to look at the Y normal stress. And then what we're going to do is we're going to inquire on a value on the outside of this geometry, on the inside of that geometry. We'll add them up, divide them by 2, take the average, and that's what we are matching, or hopefully closely matching to the theoretical results. Okay, just to explain that a little bit. What I'm going to do is uncheck the deformed model option. So we can just go up to the bar across the top, the panel across the top, turn off deformed, and that way we see the undeformed shape. It just makes it a little bit easier to select the nodes that I'm after, or the locations that I'm after. Now, I think I've probably used it before. There is a probes tool here in Nastran, and it's nice and quick. You can just click on probes, and you can move over top of the model, and it shows you different values at different locations. But what it's doing there is approximating based on your proximity to closest nodes, and we want to be precise and select this corner node and that corner node right there. So the way that you do that is you right click on nodes over here in the model tree and you say query display. And when you do that, then the values that it's showing you are just those at the nodes. And I can see that I can get midpoints too, because we do have the higher order mesh on by default. So it is able to pick up on the mid-side nodes. But let's go ahead and interrogate those values outside and inside. So we see there 1,280, right? 1,001.28 e to the 3. And over here we have 1,380. So 1,280 plus 1,380, divide that by 2. 1,330 is our average, 1,330. So if we bring back our spreadsheet over here, we can see theoretical value was 1312.5. We're going to type in our 1330, and you can see that we are within 1.3% of what that theoretical value is. So I think that's a pretty good validation, and hopefully that was a good validation model for you. Hopefully you picked up a tip or two, and thanks for watching. Have a great day.